Last exercise is about the killing vector fields and the killing equation expressed in terms of the Lie derivatives. You know that if you have the Lie derivative with respect to a vector field of G and that's equal to 0, then V is a killing vector field. Okay, so that's what we are going to check out. So the exercise is quite simple because they already gave you two vector fields to check and see if they are or not vector killing fields. Okay. So what we do? Well, let's recall ourselves what is a vector. So a vector can be expressed in terms of a linear combination of coefficients and the bases. In this case, we have two bases, the theta and the phi, and these are going to be the two coefficients that we can possibly have. And the question is the phi and the theta, are these two guys killing vectors? So let's give a look what are the coefficients for the phi. Well, what do we have here? So if we have only the phi, there should be only this guy, meaning the theta is equal to 0 and the phi is equal to 1. Same for the theta. What are the coefficients of the vector basis the theta? Well, this must be equal to 1 and this has to be equal to 0. So these are the coefficients of the phi and the theta basis. Good. So now I write down the equation. So we have the Lie derivative of our metric G and we have the components Ej, and we have to check what is the vector field for which this condition is met. Okay, so let's check out then. We have the Lie derivatives with respect to a generic vector field from before, from earlier. So JV is this one is this one, and this one is this one. Good. In this case, T is going to be our metric. Therefore, all of that is actually G, not T. Let me correct that. Tac. And then come on, right? G, and G. Okay, now I like it. Good. So what do we notice? First of all, we have in our expression, we have derivatives of the vector. So you see derivative of the vector field, derivative of the vector field, and derivative of the vector field. So what we have to do? Well, we first realize that in both cases, the derivatives of the coefficients are equal to 0. Therefore, all terms of this sort, of this fraction, are equal to 0. Therefore, if we get the first one, okay, you see that's the first expression that we derived earlier, that's the derivative of constant coefficient equal to 0. Same for the theta phi coefficient, equal to 0, that's equal to 0. So far, so good, okay? That's what we would expect for our killing vector. Let's give a look for the last one, which is a little bit more complicated, because we have two terms, one of which is the derivative of our vector field, which is equal to 0, but we are left with this term. Therefore, to obtain this condition and have this guy equal to 0, for any theta, we need this coefficient of our vector field to be 0. That's the condition to have all zeros here. Okay? Then what do we realize? Which one of the two guys here have the coefficient v theta equal to 0? Well, it's this one. Therefore, we understand that the theta phi, this one, is a killing vector field. This condition is met. Whereas this is not the case for the other vector field that we were asking to check, the theta phi, the phi. Okay, that's because the coefficient v phi is equal to 1, is not 0. Therefore, this expression is not equal to 0 in general. Okay, is not equal to 0 in general, meaning this guy is not a killing vector, is not a killing vector field. Then we can ask what are the implications for this, the existence of this killing vector, and the conclusion that we have is that this killing equation is associated to the rotational symmetry around the polar axis. Okay, so that's the association that you have between the Killing vector field and the symmetries of your system.